So we were talking about thermodynamic derivatives, and we said in particular that there were 3 of them that we wanted to express other derivatives in terms of. These 3 are the isothermal bulk modulus, the isobaric thermal expansion coefficient, and the heat capacity at constant pressure. So let's just take a couple of minutes talking about what these represent. All right? The bulk modulus could be rewritten in this way. All right? It's the pressure required per fractional volume change. Okay? A characteristic bulk modulus might be around 10 to the 10 pascals. All right? For various solids. All right? So what would that mean? Well, it would mean that a pressure of 10 to the 8th pascals, which is about 1,000 atmospheres, would decrease the volume by about 1%. So that's the bulk modulus. What about the thermal expansion coefficient? Well, once again, we can understand this constant in terms of a fractional volume change. All right? So this is the fractional volume change. Per temperature change. All right? So if alpha was 10 to the minus 6 per Kelvin, then an increase in temperature of 100 Kelvin would cause an increase in volume of 0.1%. Okay? And then we've got the heat capacity at constant pressure. All right, and so this is going to be the heat required per change in temperature. All right, so if I had a heat capacity of 300 joules per Kelvin, then 300 joules of heat are required for each Kelvin increase in temperature. All right? Now, the reason that we are spotlighting these three derivatives is because they're more or less easily measured in the lab. Okay? Constant temperature is accomplished by putting a substance in thermal contact with a reservoir maintained at a certain temperature. One way to do that is to, for example, put a bunch of ice in some water. Okay? So while ice is melting, it stays at the same temperature. All right, you may have experienced this long ago, pre-COVID, on a nice hot summer day out at a cookout where there are sodas in a container of ice. Now, on that hot day, no matter how hot it is, if you look in the container and there's still ice floating in the water, the soda is still cold. But if you look in the container and there's no more ice in there, well, then the soda's probably warm. All right? And that's because the ice in the water will maintain the temperature at 0 degrees Celsius until all the ice has melted. The water cannot increase its temperature. Any heat given to the ice water, instead of going to heating up the water, it will go to melting the ice. So we would put something in a bath at constant temperature, and we would increase the pressure on our substance and measure how much the volume changed. All right, so that's relatively easy to measure. Processes at constant pressure take place and you just have it open to the atmosphere. All right, so here I would increase the temperature of my substance, all right, measure its change in volume while just leaving it open to the atmosphere so that the pressure is constant. Here, I would add heat to the substance, measure how much its temperature increases while keeping it open to the atmosphere. Okay? So these quantities are relatively easy to measure in the laboratory. That is to be contrasted with processes, for example, that take place at constant volume. All right, if you're working with a gas, you can keep the volume constant fairly easily. But if you're working with a liquid or a solid and it wants to change its volume, good luck trying to stop it from doing that. All right? So those processes are hard to actually realize in a laboratory. Keep the volume the same. Because if it wants to expand, it's going to expand. All right? So how many derivatives are there? Well, I've got 4 state variables. Pressure, temperature, entropy, volume. If I want to form a derivative, I need 2 of those. One for the top, one for the bottom. All right? Now, obviously, dvolume by dpressure at constant temperature is just going to be the reciprocal of this. So we're not going to think of that as a different derivative. All right? So what I've got so far, I've got 4 state variables. I need to choose 2 of them to take place in the derivative, to represent changes. 4 choose 2 is 6. Now I have to decide what is being held constant. I had 4 state variables. I already chose 2 of them. So there's 2 more, all right, that I can hold constant. That brings us to a total of 12 derivatives, okay? And so our challenge now is going to be able to write each of the 12 derivatives in terms of these 3. So we've got 9 additional derivatives that we've got to find a way to write in terms of these 3 derivatives. All right? Now there are 2 main techniques that we have to do this. The first lies in Maxwell relations. Remember, the change in the internal energy is equal to dt, or sorry, is equal to T ds minus P dV. This is a change in a state variable. It's an exact differential. So now we can apply Clairaut's theorem. Remember, this tells us that the temperature is equal to the change in internal energy divided by the change in entropy at constant volume, and the pressure is equal to minus the change in the energy divided by the change in the volume at constant entropy. All right, so Clairaut tells us that the mixed partials, where they're continuous, must be equal. So we would say the temperature by the volume at constant entropy is equal to minus the pressure by the entropy at constant volume. So this is a Maxwell relation. Unfortunately, none of our standard derivatives appear in this Maxwell relation. So it doesn't seem like Maxwell relations will be very useful to us. Except I keep on referring to this as a Maxwell relation, and I keep using the plural, Maxwell relations. All right, so where could I have access to other Maxwell relations? All right. Well, it turns out that we can define other thermodynamic potentials. All right, you've already seen some of this in your chemistry classes. All right, so let's take a couple of minutes to talk philosophically about what this statement means here. When I look at this, this indicates that the internal energy is naturally a function of the entropy and the volume. If we have the internal energy as a function of the entropy and the volume, then we have the proper statement for the internal energy. This is unlike what we've seen with the ideal gas. When I write the internal energy as L over 2 nRT or L over 2 PV, neither of these give the internal energy as a function of the entropy and the volume. Now that's okay. I mean, it's still equal to the internal energy, but it's not in the appropriate form. And so what that means operationally is that I need to also be told the equation of state in order to get everything from this internal energy. If instead I had been told the internal energy as a function of its canonical variables S and V, the equation of state would be something that I wouldn't have to be told. It would come out naturally. All right? So why am I saying all this? Well, we can ask, how can we switch out one of these variables? All right, so rather than having something that's naturally a function of the entropy and the volume, could I maybe have something which is naturally a function of the entropy and the pressure? And the answer to that question is yes. Yes, we can. What we're going to do is something called a Legendre transformation. All right? The pressure and the volume are canonically conjugate. We can switch which one is the appropriate variable by introducing the enthalpy, which you may have learned about in your chemistry classes. If we take d enthalpy we would get d internal energy plus PdV plus VdP. So the enthalpy is properly thought of as a function of the entropy and the pressure. All right? Now we're going to use this to develop new Maxwell relations, but the reason why the chemists care about the enthalpy is because, remember, we said it's difficult to keep something at constant volume. Now, we were just talking about a substance. The chemists are looking at chemical reactions taking place. if you've got a chemical reaction taking place, it ain't doing so at constant volume. All right? However, if I've got it open to the atmosphere, then it will do so at constant pressure. And that means that the change in the enthalpy is equal to the heat. So that gives us direct access to the heat that went into the chemical reaction by looking at the change in the enthalpy. And that's why you get those tables at the back of a chemistry book with all the enthalpy changes. All right? Now, we're not using it for that. We're using it to get another Maxwell relation. All right, so I would say dT by d pressure at constant entropy is equal to d volume by d entropy at constant pressure. So that's going to be a second Maxwell relation. Unfortunately, it also doesn't involve any of our three. But we can see now, I hope, we can start to get a sense for the way in which these derivatives are related to one another. All right? Now, it's more or less obvious there are two other thermodynamic potentials that we can define. The Helmholtz free energy, which is defined like this. And has a differential that switches the conjugate temperature and entropy. Minus S dt minus P dV. So that gives us another Maxwell relation, ds by d volume at constant temperature is equal to d pressure by d temperature at constant volume. All right? And then we've got our last thermodynamic potential, which is where we switch both of them. This is called the Gibbs free energy. And dG would be minus S dt plus V dP. So we have our last Maxwell relation, which I'm going to put here. And finally, we've got one of our special derivatives. So this is equal to minus alpha V. All right? All right, so all that work, and all we got was one more derivative. We got a bunch of relationships. So if we just had a little bit more, a little crack, we might be able to get everything. So let's talk about another technique that we can use to relate these derivatives. So let's suppose that I wanted to get depressure by detemperature at constant volume. Okay? All right. Well, let's see. Oh, look, it appears here. All right? So this might give us access to several additional derivatives. So here's what we're going to do. We're going to think of the volume as a function of the pressure and the temperature. Why? Well, short answer, because it's going to work. All right? We'll get a feel for how this goes as we work through it. So what would this mean? Well, dV would be that, right? If the volume was thought of as a function of the pressure and the temperature, then we would get these two derivatives. All right. So, wait a minute. Hey, that's one of our guys. This is equal to minus B divided by V. Sorry. No, it's not. Minus V divided by P. Not minus B over V. All right, because it's a reciprocal. So this is going to be and how about this one? Well, this is alpha V. Just like that. So here I've got a change in pressure and a change in temperature. My change in volume is equal to this. But I wanted a derivative at constant volume. So as far as what we're interested in, the volume is fixed. So I would get that. All right? And now in order to determine my derivative, all we have to do is divide by dt. All right? So depressure by detemperature at constant volume is equal to alpha B. All right? Now, I want to caution you here because people often misinterpret what's going on here. All right? So let me take you through a thought process. Somebody could say, oh, but wait a minute. It seems like that's obvious. And aren't you off by a minus sign? Because they could say, if I multiply alpha times B, then I've got minus V times 1 over V, so those cancel. So this would be minus depressure by d volume at constant temperature, d volume by d temperature at constant pressure. So can't I just cancel the two dV's out and just write a V? Clearly, the answer is no. No, we can't do that. And that's because these changes were not taking place at constant volume. This change took place at constant temperature. This change took place at constant pressure. All right? So this is not the same thing as just depressure by detemperature at constant volume. It turns out that the difference is just a minus sign, but we can't expect that to be the case at all times. It is far safer to go through this process carefully to relate the derivatives to one another. All right? So at any rate, those are the two tools that we can use to determine all 12 of the derivatives in terms of these three, or all 9 additional derivatives in terms of these three.